Hi everyone, this video is created for education purpose only. We are studying our second year BSc Mathematics paper second, numerical methods and its application, and we are studying our unit number 4, numerical solution of first order ordinary differential equation. In this video, we are going to see another numerical method to solve first order ordinary differential equation, and that method is Euler's modified method or modified Euler's method. Now, why this Euler's have modified this method? Because in previous method, that is Euler's method, we have to take smaller value of h, and hence solution is obtained very slowly, and that's why Euler's have modified this method, and this method is known as modified Euler's method or Euler's modified method. This method is explained as follows. So for that, let us consider first order ordinary differential equation dy by dx equal to f of xy with initial condition y at x naught is y naught. You may call this as equation 1. Now the Euler's formula for y at x1 is y1 equal to y naught plus h f at x naught y naught. Now Euler's have modified this formula, and Euler's have called this first approximation of y1 as zeroth approximation of y1, and this is y1, and you have to read this as zeroth approximation of y1, and that is equal to y naught plus h f at x naught y naught. Now he have approximated the first approximation, and then using that we can obtain second approximation. Now to find more correct approximation of y at x equal to x1, the Euler's modified iteration formula is n plus 1th approximation of y1 is y naught plus h by 2 in bracket f at x naught y naught plus f at x1 and nth approximation of y1. So here is a change because the previous formula was h f at x naught y naught. So here Euler's have added this more term, and this is f of x1, and instead of y1 we have nth approximation of y1 for n equal to 0, 1, 2, etc. Therefore, if you put n equal to 0, so first approximation of y1 is given by y naught plus h by 2 f at x naught y naught as it is plus f of x1. Instead of y1 we have zeroth approximation of y1. Similarly, second approximation of y1 is y naught plus h by 2 f at x naught y naught plus f at x1. Here first approximation of y1, etc. Now continuing this way, we can obtain successive approximation of y1, that is first approximation of y1, second approximation of y1, third approximation of y1, etc. So this method is continue till no significant change occurs. That is, after some iteration, we will get n minus 1th approximation of y1 is approximately equal to nth approximation of y1. Means two successive approximations we will get, these are approximately equal, and we may call this common value as first approximation of y, that is y1. So to find y at x2, the above procedure is repeated, and we can obtain value of y at x equal to xn. So this is the Euler's modified method for successive approximation. So let us see how this method works. So for that, consider example. So given that dy by dx is x square plus y with initial condition y at 0 is 1. Determine the value of y at x equal to 0.1 by using modified Euler's method. We have given h equal to 0.05. So let us see solution. Our given differential equation is dy by dx is x square plus y with initial condition y at 0 is 1. So your f of xy is x square plus y at 0. So this 0 is your x naught. So x naught is 0 and y naught is y at x naught, and that is 1. One more thing is given, h equal to 0.05. So as we have xr is x naught plus rh, so you will get x naught is 0, then x naught is 0 plus h, that is 0.05, and x2 is 0.1. To find y at 0.1, that is to find y at x2. So that is nothing but your y2. So for that we should find y1. First we find approximate value of y1. So to obtain zeroth approximation, Euler's formula is zeroth approximation of y1 is y naught plus h f at x naught y naught. Now here we have to compute f at x naught y naught. So x naught is 0, y naught is 1. So f at x naught y naught. So this is your f of xy. So replace x by x naught, y by y naught. So you will get this is 0 square plus 1, which is equal to 1. And therefore zeroth approximation of y1 is y naught is 1 plus h is 0.05 into f at x naught y naught, that is equal to 1. Simplify this. You will get zeroth approximation of y1 is 1.05. Now we have to approximate the first approximation of y1. So the first approximation of y1 is given by Euler's modified formula, and that is first approximation of y1 is y naught plus h by 2 f at x naught y naught plus f at x1. Instead of y1, we have zeroth approximation of y1. Here x1 is 0.05, zeroth approximation we have already computed 1.05, and therefore this value is f at x1 comma zeroth approximation of y1. So zeroth approximation 1.05. So f at 0.05 comma 1.05. So f of xy is x square plus y. Simplify this, you will get f at x1 zeroth approximation of y1 is 1.0525. So put here, we have already computed f at x naught y naught. So first approximation of y1 is y naught is 1 plus h is 0.05 divided by 2 in bracket. We have already computed f at x naught y naught is 1 and this term is 1.0525. So simplify this, you will get it is 1.0513. Now the second approximation by Euler's modified formula is second approximation of y1 is y naught plus h by 2 f at x naught y naught. Instead of zeroth approximation, here we use first approximation of y1. So compute this f at x1 y1 first approximation. So your x1 is 0.05 and first approximation we have obtained 1.0513. So put all this, so you will get f at x1 comma y1 first approximation, and you will get it is 1.0538. So put this value in this formula. So you will get second approximation of y1 is 1.0513. So see this first approximation and second approximation, these are correct to 4 decimal places. So we should stop our first approximation process, and here you will observe that first approximation is equal to second approximation of y1 correct to 4 decimal places, and we will call this common value as first approximation of y, and that is y1. So here y1 is 1.0513. Thus we have y1 is y at x1. So y at 0.05 is 1.0513. Now to find y2, that is y at x2 equal to 0.1. So the zeroth approximation formula for y2 is zeroth approximation of y2 is y1 plus h f at x1 y1. So x1 is 0.05, y1 we have computed in the previous step. So y1 is 1.0513 and therefore you will get f at x1 y1 is 1.0538. So put here f of x1 y1 h is 0.05. So you will get zeroth approximation of y2 is 1.1039. By Euler's modified formula, the first approximation of y2 is denoted by this y2 first approximation and it is equal to y1 plus this formula is Euler's modified formula h by 2 in bracket f at x1 y1 plus f at x2 and zeroth approximation of y2. We have already computed f of x1 y1. So here we have to compute f at x2 and zeroth approximation of y2. So here this value is 1.1139. So put this value here. So simplify this, you will get first approximation of y2 is 1.1054. So see this is the first approximation. Now these two approximations have a major difference. So we have to find another approximation of y2. So second approximation of y2 is formula y1 plus h by 2 f at x1 y1. Here is change, instead of this y we have first approximation of y2 and that is your 1.1054. So your x2 is 0.1. First approximation of y2 is 1.1054. So using this you can find f at x2 y2 1 and this is 1.1154. So put this value in this formula. So you will get second approximation of y2 is y1 is already computed 1.0513, h is 0.05 divided by 2, f at x1 y1 we have already computed and here we have computed f at x2 first approximation of y2. Simplify this, you will get second approximation of y2 is 1.1055. So see the successive approximation. This is second approximation and this is first approximation of y2 and these are correct to 3 decimal places. So we observe that first approximation of y2 is approximately equal to second approximation of y2 correct to 3 decimal places and therefore we call this as y2 and y2 is nothing but y at x2. So x2 is your 0.1. So y at 0.1 is 1.1055. So this is the value of y2, that is y at 0.1. So this is the modified Euler's method. So only change in the formula, first approximation formula, then second approximation formula. These are some exercises. You have to solve this by using modified Euler's method. So solve these examples as we have done in the previous example. And in next lecture, we will see another method, that is Runge-Kutta method for solving first order ordinary differential equation. So let us stop here.